So we're back, I think, for Vodcast 5 or 6 on Electrochemistry, Chapter 20 in AP Chemistry. And what we're looking at here is a description of the relationship between Gibbs free energy and the voltage of a cell and the number of electrons that are flowing through our external circuit. So to clarify, remember delta G stood for Gibbs free energy, the energy available to do useful work. N will stand for the number of moles of electrons, and how you determine that depends upon the oxidation and reduction half reactions. Remember, the electron moles gained must equal the moles of electrons lost in the other half reaction. This new guy is called Faraday's constant, and it's down here at the bottom. One Faraday was an electrical researcher from early years, and so if you do something cool in science, they name a unit after you. Well, what does a Faraday stand for? 96,485 coulombs, a unit of charge, per mole. And so we're going to turn that guy into the amount of energy per volt mole. And sometimes you'll see that Faraday's constant as rounded off to 96,500. You'll see it both ways. So that next equation then is the same as the previous equation if we go back. The only thing that's different is that you do not see in the upper right of these symbols the little sort of degree sign that stands for when you are under standard conditions. So N number of moles, F is the Faraday's constant, and E with this little kind of circly guy, that's our voltage of a cell under standard conditions. So now what's cool is someone has connected how much work could you get out of an electrical cell. Here is from the original textbook, just another way of looking at this equation, and I wanted to show you again, sometimes what you'll see on problems is the Faraday's constant rounded off to 96,500 joules per volt mole, also called a Faraday. Now it says down here, according to this equation, since they put a little negative sign in front of it, if the N, which is the number of moles of electrons, has to be positive, you can't have a negative number of moles, and Faraday's constant, as you can see, is positive, then your change in Gibbs free energy is going to be a positive number if the voltage is negative. I don't know why they expressed it that way. Here's how I think of it. You know that a negative delta G means a reaction is spontaneous. And now you know that a positive voltage, E, cell potential, means that it's a spontaneous reaction. So for me, the better way to think of it is backwards from this. If the voltage is greater than 0, a positive number, then your Gibbs free energy has to be a negative number. It's a spontaneous type of reaction, which happens because of the way that we set up our half cells and how electrons naturally want to flow downhill to a lower energy position from one half cell to the other, from the anode to the cathode. So let's try a sample exercise, and what's also cool about this is that you can tie it back into even finding an equilibrium constant. So the information that's given to us here says, using the standard reduction potentials in your reduction potential table, that's table 20.1, find the delta G, the Gibbs free energy, and the K, the equilibrium constant, at 25 degrees Celsius for this reaction. Notice that we'll be doing something similar for the second reaction, but notice that the coefficients have changed. So step number 1, you have to be competent now to find out that this silver, turning from silver metal to silver ion, is being oxidized. And this water that's forming over here must have happened from the reaction of oxygen in an acidic solution, and so now we have our reduction half reaction. The numbers of electrons are already equal to each other. That is the N in the equation that we're getting ready to use. But now that we've pulled off the two half reactions, you go to a reduction potential chart and you find the voltage for the, in this case, reduction half potential or half cell, and you get the voltage for the oxidation half cell. Now they've written it here as an oxidation, but if you go to the chart, you'll see it written backwards with this voltage next to it. So if you're going to find the change in the voltage of the cell, remember it was simply cathode minus anode. So here's the cathodic reaction, positive 1.23 volts. Here's the anodic reaction, 0.8 volts. The difference between these two is the cell potential, or the voltage, 0.43. It's positive, so it's spontaneous. So now we take a look at that new equation we just learned, how Gibbs free energy can be connected to the number of moles of electrons times the Faraday's constant times the voltage. Well, the number of moles of electrons is 4. That's 4 moles, not 4 electrons. The Faraday's constant was given to you on those previous slides. You could either use 96,485 joules per volt mole, or you could just use the Faraday's constant. And the voltage is 0.43, found from up here. Notice that Faraday's constant is in joules, and they weren't very good about it. They should have put the number, after the number 4, they should have put the word moles, so the moles will cancel. And you would have also had the joules canceled out. So essentially you end up, not cancel out, you end up with the number of joules per volt. That's the unit that's down here. So our value is a negative value. It's expressed in joules, but we want to divide by 1,000 because delta G's, Gibbs free energies, are always expressed in kilojoules. So that makes sense. You have a positive voltage, it's a spontaneous reaction, the delta G should be a negative number. Pretty much that's about it for these voltage, number of moles of electrons times Faraday's constant times the voltage. Take the negative value of that, and that will give you your Gibbs free energy. Now the second equation that you have to use to find the equilibrium constant, the K, was one from chapter 19. This equation that you see right here is taken directly out of the latter part of chapter 19. Chapter 19 says if you know your Gibbs free energy, well, we just calculated that, and you have your gas constant, we have to use the 8.3 value because they're going to be in joules. That times the temperature, that has to be in Kelvin, which was specified standard conditions 298 K, times that by the natural log of the equilibrium constant. So let's take a look at what we know. We know the delta G, which now they've turned back into joules again, because the gas constant you have to use is also in joules. And we know the temperature. So if we have 3 known values, the only thing missing is the natural log of the K, the equilibrium constant. Algebraically rearranging that equation, we plugged in our numbers. We found that the natural log of K equals 69, and now you have to take the anti-log, the inverse of a log, to turn 69 into a very large equilibrium constant, 9 times 10 to the 29th. In common sense terms, what that means is, if you go back and look at the previous reaction, they're putting some silver in acid. And so there's a high probability that it's going to drive to the right and make silver ions. That's what acids do to metals. So that is how you can go all the way from using all of your skills together, your knowledge of thermodynamics, your knowledge of equilibrium, and your knowledge of electrochemistry to solve for all of the values that were given to you in this problem. Now I know that I've emphasized in previous problems that we talked about voltage being an intensive property. It's not a function of the number of multipliers or coefficients that you have in an equation. But let's see what does vary. In the second overall reaction, it looks just like the original one, except you'll notice that all the coefficients have been cut in half. We still go and get the same oxidation and reduction half reactions. We go and look at the reduction potential chart, and we still find out that the difference between the two voltages, even though the cathode minus anode is how we determine the potential of the cell, even though the coefficients have changed, the voltage of the cell hasn't changed. But it doesn't take too much to think about what did change, and what did change was here, the number of moles of electrons. So when you are plugging that into delta G equals negative N times F times E, the N changed. The Faraday's constant stayed the same, and the voltage of the cell stayed the same. So the value that you should get is going to be less than before, negative 83 kilojoules per mole. And I forgot what it was up above. That's our delta G somewhere up in, let's go back. Oh, up here. Negative 1.7 times 10 to the 5th joules, or negative 1.7 times 10 to the 2nd kilojoules. And so that's why this number is half of the original delta G, because you have half the number of electrons flowing. So if you now take the second equation to find the equilibrium constant, delta G, which is now negative 83 kilojoules per mole, here it is turned into joules, equals negative R, gas constant, times the temperature, 298, times the I don't know, natural log of the equilibrium constant. Now you have a value that is substantially less. And that's because the number of electrons have changed. So when you change the number of electrons, it doesn't impact voltage, but it could impact your Gibbs free energy, and it will impact the value of your equilibrium constant. So that's kind of a cool thing where you can put all three of those factors together: equilibrium, thermodynamics, and electrochemistry. And I just spoke about that. So that's a good stopping point for this first mini vodcast. What I'm going to recommend that you do is continue on to the next mini vodcast if you have time, and we'll learn how to calculate the voltage under non-standard conditions using something called the Nernst equation. Take care.